In this video, we're going to start talking about exceptions to the octet rule, which we've talked about in many other videos. The octet rule is this notion that atoms tend to react in ways that they're able to have a full outer shell. They're able to have 8 valence electrons. Now, we've already talked about some exceptions, things like hydrogen. Its outer shell is that first shell, which gets full with 2 electrons. So it's trying to get to that duet rule. But as we'll see, there are other exceptions. Boron and aluminum, for example, they can form stable molecules where the boron or the aluminum only have 6 valence electrons, not 8. And there are exceptions in the other direction. As you get to the third period and beyond, we'll actually see atoms that can maintain more than 8 valence electrons. And we're actually going to see an example of that with xenon. So let's just go into a few examples. Given what I've told you, see if you can come up with the Lewis diagram for aluminum hydride. So aluminum hydride has 1 aluminum and 3 hydrogens. See if you can draw the Lewis diagram for that. All right, now let's do this together. So the first thing you want to do is account for all of the valence electrons. Aluminum's outer shell is the third shell, so in the third period here, and it has 1, 2, 3 valence electrons. And then we have 3 hydrogens, and each hydrogen has 1 valence electron. And so you add all of this up together. 3 plus 3 is equal to 6 valence electrons in aluminum hydride. Now, the next step after that is to try to draw the structure with some covalent bonds. We don't want to make hydrogen our central atom. That would be very atypical. And so let's put aluminum in the center. And then we're going to have 3 hydrogens. So 1, 2, and 3. And then let's put some covalent bonds in here. And so let's see, how many valence electrons have we now accounted for? This is 2 in this covalent bond. Another 2 gets us to 4. Another 2 gets us to 6. So we have just accounted for all 6 valence electrons. So we have no more valence electrons to play with. Let's think about how the various atoms are doing. So the hydrogens are all meeting their duet rule. These 2 electrons in this bond are hanging around hydrogen and around the aluminum. But from hydrogen's point of view, it has a full duet. And that hydrogen as well, and that hydrogen as well. But notice the aluminum over here, it has 2, 4, 6 electrons, valence electrons around it. And so it's not a full octet, but aluminum hydride is actually something that has been observed. Let's think about another example. Let's think about xenon pentafluoride cation. So a positively charged ion here. Pause this video and see if you could draw the Lewis diagram for this. All right, now let's do this together. If any of this seems unfamiliar, I encourage you to watch the video on Introduction to Drawing Lewis Diagrams. But what we'd want to do here is first think about our valence electrons. So xenon right over here, it's actually a noble gas. It already has a full octet in its outer shell. So it has 8 valence electrons. So xenon has 8 valence electrons. And then fluorine, we've seen this multiple times, has 1, 2, 3, 4, 5, 6, 7 valence electrons. But there's 5 of them. So 5 times 7, I'm going to be drawing a lot of electrons in this. So this gives us a total of 8 plus 35, which is 43 valence electrons. But we have to be careful. This is a cation. It is a positively charged molecule. It has a positive 1 charge. So we have to take 1 electron away because of that. So let's take away 1 valence electron to get that cation. And so we are left with 42 valence electrons. So the next step is to try to draw its structure with some basic single covalent bonds. And xenon would be our preferred central atom because fluorine is more electronegative. It's actually the most electronegative element. So let's put xenon in the middle. And then let's put some fluorines around it, 5 of them to be specific. So 1, 2, 3, 4. I'm having trouble writing an F. 4, and then 5 fluorines. And now let me make 5 covalent bonds. 1, 2, 3, 4, 5. So just like that, I have accounted for 10 valence electrons because you have 2 valence electrons in each of these covalent bonds. 2, 4, 6, 8, 10. So let me subtract 10 valence electrons. And then we are left with 32 valence electrons. Now the next step is to try to allocate some more of these valence electrons to the terminal atoms so that they get to a full octet. So let me do that to the fluorines. Each of these fluorines already are participating in a covalent bond. So they already have 2 valence electrons hanging out with them. So let's give them each 6 more. So let's give that fluorine 6, and that fluorine gets 6. And that fluorine gets 6 valence electrons. And that fluorine gets 6 valence electrons. And then last but not least, this fluorine gets 6 valence electrons. So I've just given away 6 valence electrons to each of 5 fluorine atoms. So that is 30 valence electrons that I have just allocated. And then what does that leave me with? And that leaves me with 2 valence electrons that have gone unallocated. And the only place to now put them is on the xenon. And as I said, things that are lower down in that periodic table of elements, especially as we get below the 3rd period, these can defy the octet rule. Xenon already has 10 valence electrons, and I'm about to allocate it 2 more to it, just like that. So you allocate those 2 more, and then we have allocated all of our valence electrons. And I want to make sure I remind myself and everyone that this is a cation. So I have to put that plus charge just like this. But this is something that has been observed, where you can actually have a central atom like this that goes beyond an octet number of valence electrons. In this case, it has 2, 4, 6, 8, 10, 12 valence electrons. Now, an interesting question is, how do these atoms that are in the 3rd period or beyond handle more than 8 valence electrons? And it is a matter of debate, but some chemists believe that it's possible because they're able to place their electrons in their empty valence d orbitals. But once again, this is controversial in the chemistry community.